Good afternoon, dear participants of the conference. My name is Sergiy Gnatyuk. I'm from National Aviation University, and I want to present you uh, my presentation. Uh, my topic is studies on the disaster criticality assessment in aviation information infrastructure. So the implementation of the modern information and communication technologies in different sectors of critical infrastructure of the state causes the improvement of the efficiency of various business process. But in another hand, we have a lot of cyber incidents, cyber attacks, and cyber threats. So different critical infrastructure sectors need new approaches to provide the cyber security of the sector with some requirements to speed and the security. The civil aviation is one of the most critical sectors of state infrastructure, and the criticality of civil aviation amplified by the high level of connectivity between on ground and on board systems in aviation. So the methods for some critical components or items assessments is very critical because very important because we can use these methods to rank some critical items, maybe some systems or some sectors, and firstly provide the cyber security for the most critical items. First of all, we have analyzed modern methods of the calculating the criticality of information systems, and these methods you can see on the table number 1. And we have analyzed 10 methods, and we have defined that the most effective system is FMECA. For the analysis in table 1, we have used the following criteria. The first one is detection of work or danger interruption. Next is analysis of ways to detect the causes of interruptions in work, consequences forecasting, determining the criticality of each type of work or danger interruption, minimize or eliminate the effects of work interruptions, and impact assessment on the work and risk assessment. This is the last criterion. By the way, the main purpose of this work is experimental study of the method for importance level assessing for critical information infrastructure objects in aviation, named CAIS, based on the criticality analysis of the systems or subsystem disaster risks. This method was proposed by authors before, and it is based on the FMECA technique with proposed improvements for the effective quantitative and qualitative assessment. FMECA technique requires the identification of the following basic information: items, functions, failures, effects of failures, causes of failure, current controls, recommended actions, and other relevant details if they are needed in some cases. Previously, we have proposed a method for criticality assessment in aviation and other sectors of critical information infrastructure, and this method is described in the next few slides. The first stage of this method is determining the system components and setting the detail level. And this stage consists of 5 steps. The second one is determining the functions of each detected system component. Third stage is determining the list of possible work interruptions for each system component. Next is determining the consequences of each possible work interruption. Stage number 5 is identification of sign of interruptions for work detection. The sixth is identification of method to detect work interruptions. 7 is construction of three-dimensional matrix of criticality. The example of this matrix you can see on the figure number 1. Stage number 8 is calculation the criticality rank for probable interactions, and this stage consists of the 5 steps. And next is identification the list of the most significant or critical work interruptions, and you can see the formula number 2 that describes the mathematical model of the most critical work interruptions identification. Next sub stage is the building of a Pareto chart. This chart helps to select a list of the most significant interruptions for some items, as well as make it possible to compare individual items by calculated interruptions and select the items with a more critical for some critical aviation information system. The next stage is tense formation a list of corrective measures. And in this stage, we have proposed the cause effect Ishikawa cause effect chart. The example you can see on the figure number 3. This chart separates all defined interruptions for the main reasons of their occurrence due to, for example, users errors, software, hardware, network technology errors. And the example of the list of corrective measures. You can see on the table number 2 in this slide. This is the general interpretation of the of this stage. And the last stage is reporting. At this stage, the systematization of the data is concluded, which obtain the all previous parameters from the items identification to criticality rank calculation. And the example of this report you can see in general interpretation on the table number 2. We have analyzed 3 different systems from civil aviation, and we have received the following results. You can see the results from for 2 or 3 experiments on this slide, and you can see a three-dimensional matrix. You can see Pareto chart and Ishikawa chart, and also on the right corner you can see the report for all level of the analysis for these systems. The most critical system is TCAS. TCAS system is aeronautical system, critical aviation information system, and the reporting from the output data of our proposed method for this system you can see on this slide. And the most critical items are highlighted by a gray color, and you can see this on the right side of the table. The main metric in our method is criticality rank, and it can be used for critical information infrastructure ranking. Experimental study gives possibility to determine the importance level of 3 systems, as I have said: the aeronautical information processing and transmission system, onboard collision avoidance system, and system Amadeus for the ticket booking. We have analyzed all these systems, all items of this system, and we have received the following results. As you can see on this slide, the first system has only 1 critical component with 1 functional interruption. Second system has 3 critical components and 5 functional interruptions, and the last system has 2 critical components and 3 functional interruptions. 3-dimensional criticality matrix and Pareto bar chart show that TCAS system is the most critical and most selected. It has 5 critical interruptions, and Ishikawa diagram shows that priority areas for the developing corrective measures for the first and third system are elimination of software errors and user errors. For the most critical system, TCAS, elimination of hardware and software related causes. In this paper, uh, uh, we have presented experimental study of previously proposed FMECA-based method for importance level assessing of critical information infrastructure objects in aviation, based on critical analysis of the systems or subsystems risks, disaster risks, was carried out. It was selected three critical aviation information systems, and this system were used for experimental study. Three-dimensional criticality matrix um, shows that TCAS is the most critical system, and Ishikawa diagram shows the way to improve the security level of the TCAS system. In the future research study, it is planned to develop software that based on the proposed method and will allow to conduct and experimental research and confirm the possibility of determination the importance of different categories of critical aviation information systems, and as to assess infrastructure risks in different industries, not only aviation, but for example, we can use power energy, communication, uh, gas and oil industry, and so on. That's all. Thank you very much for your attention. If you have any questions, I'm ready to answer it. Thank you.